Hello everyone, I am Ziyue Qiu. I'm here to present our paper titled FrozenHot Cache, Rethinking Cache Management for Modern Hardware. This collaboration is between the University of Science and Technology of China, Microsoft Research, CMU, and QCRI. Our research is based on the recognition that list-based caches are the dominant type for in-memory software caches today, and they are managed by popular algorithms such as LRU, FIFO, and certain variants of LFU. Application accesses go through a cache lookup, which is accelerated by a hash table in common implementations today. A hit is followed by read, while a miss or an application write is followed by insert. With either a hit or a miss, we typically need to perform cache management by adjusting the ordering of objects in a doubly linked list. For example, with LRU, the hit object becomes the most recently used one, so it's then pulled to the head, or MRU end. And the LRU end is the candidate for the next eviction. The problem is, each of these operations involves log. For insert, we have contention at both the head and the tail. For lookup, the LRU promotion has contention at the MRU position and requires log protection too. What happens is that such internal operations are update intensive and contention heavy, even when the application workloads are cache-friendly and read-only. This is particularly problematic with the increasing concurrency level with higher core counts per node. Let's see some hit latency measurements. With growing number of threads, where the bars marked by letter O give original LRU results, using the meta HVM LRU cache. At one thread, hit latency isn't an issue. Even under 20 threads, it is still under 1 microsecond. Comparing this latency with that of mechanical drives, we still enjoy a 3 orders of magnitude improvement with a cache hit. However, machines today have more cores and faster storage. For example, AMD now supports up to 192 threads per socket, and NVMe SSDs achieve microsecond level latency. As the number of threads grows to 80, hit latency skyrockets. It is close to half of the SSD read latency. In the bars, the gray block shows lookup and the white block shows management overhead. Both grows together with thread count, and the management overhead dominates the hit latency at 80 threads. In this work, we propose FrozenHot, a new in-memory cache design for scalability. To give a performance sneak peek, under 80 threads, FrozenHot reduced 87% of hit path overhead by removing management and speeding up hash lookup. Before delving into the more detailed FrozenHot design, let's examine today's workloads targeted by in-memory caches. With cache-friendly workloads, most of the list maintenance just shuffle hottest objects in their popularity contest, close to one end of the list, namely the top. Most of such reordering wastes cycles and creates contention without making much impact on the list itself. Meanwhile, cache-unfriendly workloads often exhibit scanning patterns. In this case, most of the scanned objects are similarly coded, and it's pointless to order them. When we have cyclic scans, list management harms the hit ratio by thrashing. Let's imagine a cache that can hold 80% of the objects in such a cyclic scan. Every access becomes a cache miss, since no objects can get hit by the next scanning loop before they forcefully get pushed out of the cache. So with these workloads, continuous management offers no benefits and may even be harmful. With FrozenHot, the cache is split into a static, frozen cache, the FC, and a dynamic cache, the DC. The FC, holding the hotter objects, performs no cache management at all, while the DC operates with the original list-based maintenance. The two linked lists concatenate into a full list of all items cached. The FC and DC also have their corresponding hash tables. Here, the difference is that the DC hash contains all cached objects, while the FC hash only contains the subset belongs to the FC, for simplicity of FC destruction in the future. Let's look into the FrozenHot operations. Still, the application sends lookup and insert requests to the cache. But the insertions and evictions only occur in dynamic cache. A lookup first goes to frozen cache and usually just returns from there. But if it's a frozen cache miss, we will then do lookup in DC. Such FrozenHot design has multiple sources of performance savings. A fundamental change is that for the majority of cache hits, we get rid of cache management entirely. This means that we greatly simplify the hit path and do a lot less work. There are two other implications. First, without cache maintenance, for the FC, we don't have the contention and therefore don't need to use locks anymore. Second, the FC hash is now read-only, which allows us to adopt much faster hash table implementations. However, we can't simply freeze a part of the cache forever. Instead, FrozenHot alternates through three phases. A learning phase, where it serves with a merged cache and makes performance observations. A construction phase, where it continues to serve the application while building the FC hash in background. And finally, a frozen phase where it serves with the split cache. Typically, the frozen phase lasts much longer than the other two. With such a life cycle, the FC needs to be periodically rebuilt. Conceptually and physically, its construction is by splitting the doubly linked list, which can be done in constant time. Then, while the combined cache serves application requests, we construct the FC hash in the background, and the FC can be frozen. The instruction is basically merging FC and DC, where we simply discard the FC hash and relink the lists, again in O1 time. Here, you can see that FrozenHot doesn't care how the objects are ranked. It just splits and merges the list. So in this way, we can support all list-based caching algorithms. Now comes the hard question. Where does FrozenHot need dynamic decision-making? Actually, two dimensions. Spatially, in each learning phase, we need to decide how much and which part of the cache to freeze for the next frozen phase. Temporally, we need to know how long that frozen phase should last. In the space dimension, the which question boils down to simply picking the value of k. Since we don't have to worry about the ordering rules here, we just follow the rules. So how to pick optimal k? This figure illustrates the relationship between the FC ratio, the ratio of frozen cache size, and the overall hit ratio. The pros here is that the more objects frozen, the more hits we see in the FC, shown here with the blue curve. However, the cons is the overall hit ratio likely goes down a little bit, as shown by the green curve, because larger part of the cache becomes static. Thus, we can identify the optimal setting somewhere in between the no FC and all FC. For example, when we calculate the average latency, the red dotted curve, we find the optimal is around 30%. For the time dimension, during each frozen phase, the controller monitors the FC operation and the overall performance, and decides to defreeze when a performance degradation beyond a certain threshold is observed. Now, let's discuss the evaluation. We implemented FrozenHot for 3 popular caching algorithms: LRU, FIFO, and LFU. Note that the LRU baseline used here is already an overhead-optimized version for production usage. We call this a relaxed LRU. For test workloads, we use a total of 19 traces from the Twitter and MSR Cambridge. First, this figure shows the throughput improvement brought by FrozenHot to original implementation, with varying concurrency level from 1 to 72 threads. The box shows the 25th and 75th percentile distribution, with whiskers extending to the mean and max. The red line shows the median speedup, and the blue dotted line indicates the 0% speedup. As expected, the more threads we have, the larger the benefit. With MSR workloads, we see up to a 3.4 times throughput and 1.4 times in average. Also, FrozenHot shows more benefit with workloads that yield higher hit ratio. Intuitively, since they can save more from our hit path optimization. See the Twitter results on the right. We achieve up to 6.5 times throughput and 2.2 times in average. In our paper, we have detailed breakdown analysis of the improvement as well as timelines of different phases. And due to the time limit, we only feature one more set of results on how much of the cache gets frozen. Here we use stacked bars to show, for each workload, the portion of time spent at each frozen ratio range. 0, which means no FC, only baseline cache, below 0.3, between 0.3 and 1, and exactly 1, where the whole cache is frozen. In addition, the gray bar gives time spent in the learning phase, where the controller observes things and makes decisions. In this particular example, we have Twitter 45 trace using LRU FrozenHot, with a pair of bars showing results at different concurrency levels, 20 threads on the left and 72 threads on the right. As one can see, FrozenHot decides to freeze nothing at 20 threads, but everything at 72 threads. In general, higher concurrency leads to higher frozen ratio for the same workload. When we take a look across the Twitter traces, we make the second observation. The frozen ratio selected is highly workload dependent, mainly by the workload patterns, like locality and how dynamic the hotspots are. Surprisingly, under MSR workloads, which often show poor locality and therefore lower hit ratio, the controller actually often ends up choosing a 100% frozen ratio, as it finds frequent cache management meaningless. In a few cases, where the workload have cyclic scan behavior, freezing the entire cache significantly improves the hit ratio as it reduces thrashing. To conclude, this work finds that software in-memory caches need redesign for modern trends. Continuous full cache maintenance is just wasteful. As a solution, we propose FrozenHot, where we split the conventional in-memory cache into a periodically rebuilt frozen cache and a live updated dynamic cache. Our work is open sourced, and we are more than welcome to any follow-up discussions. Thanks for listening.